All right, class, welcome back. So this is an ALEKS topic that's called Standardizing a Base Solution by Titration. And I think this is a great review type topic, or another way to say that would be a topic that puts together a lot of great information that we should have a good grasp of as we move into the next chemistry series. So in this question, there's a lot of information. And the first thing that we want to do is obviously start with a balanced chemical reaction. So anytime we're sort of given, we look at this initially and we're like, oh my gosh, there's like so much going on. Start organizing the information and then worry about what the question's actually asking. So the first thing that I would do is I would say, we've got oxalic acid, H2C2O4. I'm going to write that down, right? So H2C2O4, we're told that that's a diprotic acid. So a good indicator here is that I've got H2 in the very front. When we sort of see that, that's going to be, these are the acidic protons. They're going to be coming off as H+. They can react with OH- to form water in our neutralization reaction. But in this, sort of the way that it's written out here, it does suggest it's diprotic. It also tells us it's diprotic. So two of these are going to come off to react with our sodium hydroxide. So I know right away, and really this is just because I have experience doing this, that if it's a diprotic acid and I'm going to be reacting it with sodium hydroxide, so down here, I'm going to be reacting that with the sodium hydroxide solution, I know that I'm going to need two equivalents of sodium hydroxide because every one sodium hydroxide has one OH. That's what's going to be reacting with the H+. So here, this is our acid. That's going to react with the OH- to form H2O. And since we've got two, right, diprotic, and then two sodium hydroxides, I'm going to end up with a 2H2O. So I'm sort of writing the reaction and balancing at the same time. You don't have to do this, but it definitely, once you get the hang of it, it will help you out. If you see triprotic, it's going to be 3 sodium hydroxide. If it's monoprotic, obviously just 1 sodium hydroxide. So then our other product here is going to be Na2C2O4. We could put phase labels in here, if we wanted to, aqueous, aqueous, liquid, aqueous. Not totally necessary, but good to keep in mind. Okay, so now I've got a balanced chemical reaction. That's going to be sort of what happens in this problem. But I'm also going to draw a little picture because I think that in a lot of these types of problems, sort of visualizing what's going on is sort of the hardest part. So I'm going to draw a titration setup that looks like this. So this is the reaction, the way that it's going to be set up. So I've got my sodium hydroxide in a burette, and I'm going to be dripping that sodium hydroxide into my reaction flask, and my reaction flask has that H2C2O4. So that's going to be sort of what's going on in this reaction. I'm going to be adding the sodium hydroxide until I get to that end point. Once I get to that end point, that's going to be, the equivalence point. That's going to be when my moles have completely canceled out. So that's going to be when all of the moles of H2C2O4 that I start with down here has been reacted by the sodium hydroxide. And this 76.5 milliliters, that's going to be relevant for this problem. So here we're going to have 196 milligrams, also known as 0.196 grams. So just doing that quick conversion for simplicity's sake. And then we're told that it's dissolved in 250 milliliters. I think we get confused by this quite a bit. This 250 milliliters of distilled water, it's actually totally irrelevant. That's going to be saying we're going to have 250 milliliters in this flask down here. But if you put more water in here, yes, the molarity will change, but the number of moles will not. And that's really what we're concerned with, is how many moles of H2C2O4 do I start with? Because that's going to equal the number of moles, right, of sodium hydroxide that we need to get to that equivalence point. So really, this 250 milliliters is totally irrelevant. If it was 50, it was 100, it doesn't matter because the number of moles of H2C2O4, that's what's going to be important. That's what's going to stay the same. And then we're going to equate that number of moles to the sodium hydroxide to figure out what my molarity of the sodium hydroxide, that's what we're actually looking for, what my molarity is. So all of this organization, we're 4 minutes into this video and I haven't even thought about, what I'm going to do, right? I'm just organizing the information, balanced chemical reaction, get everything in place. Okay, so now I'm going to go ahead and figure out, if I've got a number of grams of my acid, I could calculate the molar mass, which is 90.04 grams per mole. Then I can figure out how many moles of that acid, right? I said that was the important part, is how many moles of this H2C2O4 you're going to have, times 1 mole over 90.04 grams. And that gives us 0.002177 moles of our acid. So C2O4. So that tells me that in this reaction flask down here, I've got this number of moles of H2C2O4. And then I want to use my balanced chemical reaction to figure out how much sodium hydroxide, how many moles of sodium hydroxide am I going to be putting in there. So we might just look at this and know, oh, I've got to multiply by 2. But it's a good practice to write this out, to write out all of your conversions, because then you don't make silly mistakes like dividing by 2 when you should be multiplying by 2. And I know that we've all done that. So if I have 0.002177 moles of my diprotic acid, I'm going to do a mole-to-mole conversion. For every 2 moles of sodium hydroxide, we use up 1 mole of our acid. I can see my unit conversions here. My moles of acid will cancel out. And that tells me at the equivalence point, I will have dispensed the number of moles of sodium hydroxide, 0.004354 moles of NaOH. So that tells me how many moles of sodium hydroxide did I put into my reaction to make this reaction go to the equivalence point, right, to complete the reaction. So if this is my number of moles, and we know the volume of sodium hydroxide that we dispensed, well, now we can calculate the molarity, right? Molarity is just going to be the moles equals moles over liters, so that should equal 0.004354 moles of sodium hydroxide divided by 0.0765 liters. So I'm just converting this 76.5 milliliters into liters. And I got a final value here of 0.0569 molar sodium hydroxide. Now, once we have this answer, right, we could work backwards to say, well, if this is my number of my concentration, how many moles of sodium hydroxide would that be? If I've got that number of moles of sodium hydroxide, which we should find is this number, how many moles of acid can we react with that number of moles of sodium hydroxide? So all of this, right, in either direction should make complete sense and should get us to the correct answer, right? Back and forth, back and forth. Okay, hopefully that makes sense. Definitely, if you've got any questions about this, let me know. Cheers.